Data was donated to the UCI Machine Learning Repository website, and the attributes cover a range of information, including demographic, medical record, and various survey answers to questions evaluating sexual health and smoking habits. For this project, I'd like to be able to predict cervical cancer using the binary target variable called biopsy. Cervical cancer can go undetected for a long period of time if a woman does not receive routine screening. A biopsy is the most definitive way to identify presence of cancerous cells on the cervix. So in order to improve early detection in a data-driven way, I'd like to build a model that classifies whether or not people have cervical cancer based on the 35 attributes provided in this data set. In our approach to modeling, I'll prioritize improving the false negatives, so making sure that members with cancer were correctly identified. To do this, we'll create 3 models, evaluate their performance individually, and then determine if there's a way to string these models together using a stacked approach that might improve accuracy. So let's take a quick look at the data. I'm importing it and then printing out the prevalence of the endpoint. So there are 55 women with cancer. There are 35 predictor variables, and the endpoint, which is biopsy, and 858 observations. Okay, I do suspect that there is some collinearity between the Hinzelman, Schiller, and cytology tests, which are all tests for cervical cancer. And since these tend to be performed together, at least one after another, let's take a look at them with the pairs.panel function, which I've already run here. So it looks like Schiller and Hinzelman tests are in fact collinear with a correlation of 0.65. That means that positive results from these tests tend to occur together. So this makes sense since during a Hinzelman, it's standard procedure to use a Schiller test. So in order to identify areas of concern, you might run the Schiller test while observing the cervix through a Hinzelman test. Knowing that these two variables are highly correlated and happen during the same procedure, we might want to combine them. So let's do that. We'll combine them into a variable called colposcopy. All right, and we'll remove the variables themselves, Hinzelman and Schiller. Now let's look at distribution of the other variables real quick. You can see there are a lot of NAs in this data set, so we'll have to do some imputation here. You might also notice that some variables are zeros, such as this one, so we'll have to remove those as well. So let's do that here. So I have created this function that will calculate the mode of an input vector. Then I created an impute function that will use an if-else statement to impute the mode if the value is NA. Next, I created a variable for 5-year age grouping starting at 13 and ending with 43, which is proper childbearing age. Then we calculate the mode number of pregnancies for each age group and apply the imputed mode value for each age group since the number of pregnancies you have tends to vary greatly upon your age. And then we impute zeros for time since first and last diagnosis, and a slew of other variables that have a minimum of 1, which might imply that missing values might actually be people who have not been diagnosed with an STD or do not use birth control or who have never smoked. And we also see an imputation for the mean age since first sexual intercourse. Okay, and then looking at the distribution, it looked like all of these NAs were fixed and imputed correctly. And we should also take a look at the distribution of continuous variables, just to make sure that there isn't anything that looks extremely skewed here. So let's just play these for good measure. Okay. So several of these distributions do appear to be normal. Some of them have a lot of zeros and then a tail. Let's see what happens if we try to fix or apply a log transform to this one, hormonal BC years. All right, and it didn't really improve. So moving on, we'll just leave the data, the continuous data as is. Transformation likely won't help here. Now let's see if there is a potential linear relationship between the variables and the biopsy outcome. So we'll play that. And it looks like the only strong linear relationship is between colposcopy and biopsy, which makes sense since colposcopies are typically performed immediately before a biopsy. This is a good indication that linear regression will not fit the data very well. Our next step is to determine our modeling approach. Given the binary endpoint, we're going to explore a few binary classifier models. First, we'll look at the decision tree model, which is well suited because they can handle large amounts of data in many columns and are very transparent about their output. So we can learn a little bit about the variables and features that are most important to the endpoint. Second, we'll try a naive Bayes classifier, which is very good with large number of inputs that are mostly binary. And then I'd like to test a black box method, so a neural network might be a good route for this analysis to show complex relationships that might exist between these variables. Okay, and in splitting the data up into test and training, it's randomly sorted, so we'll just take the first 70% of the data for training and the last 30% for testing. So let's run that. And we also want to see that the endpoint is about the same in terms of prevalence for both the training and testing, so about 6% in the training data set have cancer and 7% in the test data have cancer, so that's good. All right, and we'll train our decision tree model predicting whether or not you have a positive biopsy result. And let's look at the summary. Okay, so it looks like the first split was on colposcopy. Patients with a negative result were classified as not having cancer. For those with a positive result, there was another split on the number of pregnancies. And then patients with greater than 5 pregnancies were classified as not having cancer. For patients with less than or equal to 5 pregnancies, there were 2 more splits on smokes packed per year and age of first sexual intercourse. So let's test this model on the holdout data. We've already run this, but okay. All right, the model was 96.1% accurate. Only 3 of the test patients with cancer were misclassified, which is great. This model is already extremely accurate, so it's doubtful that boosting will improve the results. So let's just check that a series of different parameters being tested with tenfold cross-validation might not give a better result. Let's just run that here. This shouldn't take too long. Okay, and the best model according to the train function has a parameter value of 1 trial. So as expected, adding trials doesn't really improve our accuracy. And let's test it here. Yep, so it's very similar in performance. So we'll just stick to our tree model as is. Moving on to naive Bayes model. We'll use the same training and test split, and we'll just train this on our training set. The model is 85.3% accurate on the training set, so let's look at our test data, applying it there. Okay, 81.8% accuracy. This model may be less accurate overall, but it did a better job at classifying true positives for cervical cancer. The downside being that there are 46 false positives now. Okay, let's see if we can tune the model to perform any better using the train function. I actually think this might take too long to run, so let's pause there. Let's see what happens if we run just the 2 lines here from what we've already done. Okay, yes, so not using a Laplace estimator and using a kernel equals 2 is the best model. Let's see if our results improve using this trained model. All right, 92.6% accuracy, but it doesn't really predict any cancer patients as having cancer. So we'll stick to our original model for naive Bayes. Next, we'll train the neural network. We have to normalize our data first before we input it in there into the neural net. This is important so that the variables don't have a biased impact on the prediction if they're continuous. We're normalizing on a scale of 0 to 1, and it looks like it worked. So we'll train our neural net, apply it to the test set. So it looks like the model was 91.5% accurate, which is pretty good. 12 patients with cancer were not classified as having cancer, though. So let's validate this and see what happened when we test several parameters, including more hitting nodes. I'm not going to run this. It might take forever, but we've saved our result here. Okay. So again, using the train function, it says having a size of 1, so 1 hidden node in the decay of 0.1 is the best model. Let's see if our results improved using this new model. And yes, okay, so it predicts the endpoint 100% of the time, which is pretty impressive. So we'll combine, we'll look at the accuracy of all three of these models. Having an AUC closer to 1 is better, and having an ROC curve in the left hand corner is better. We see for the neural net, we have 100% accuracy. The decision tree, we see 90.3% accuracy, and I'm sorry, naive Bayes, 90.3% accuracy. Nope, the opposite. Tree, 90.3, 89.8 for naive Bayes. And then when you look at the ROC, that's reflected here. So the tree model performs pretty well. Naive Bayes a little worse. And then the NNet is near perfect. So great. And we can actually try to string these models together. We'll start with maybe bagging for the tree model. So again, let's skip running it. It might take too long. So we perform bagging with the tree model. We get 95.3% accuracy, very similar to what we had before, so no improvements in performance there. If we perform bagging here, yeah, it's going to take far too long. So let's see what happens if we just run it on our saved results. So when we ran this earlier, the model has 92% accuracy when we bag on the naive Bayes. Okay, yep, that held true. And our best model for naive Bayes previously was 81%, but when we bag, we lose the accuracy in predicting those with cancer. So we'll stick to our original model results and not do any bagging here. Since we didn't have the opportunity to do regression at all, let's use a logistic model as our meta-classifier when we string these models together. So as you can see, we string the results together from the three different models, and then we'll run them on the test data, the test stacked. So let's do that now and see what the confusion matrix has to say about our new ensemble. All right, so 95.3% accuracy, which is pretty great. It predicts 14 out of the 21 cancer patients correctly. So even though we had some instances where the individual models outperformed the stacked model across the board, it's important to remember that stacked models are much less prone to bias, and it's likely more generalizable than any of the models alone. Additionally, each of these models recognizes unique and subtle patterns within the data that we surely would want to capture when applying to a broader population. It's suspicious that the models were so accurate, and this makes me skeptical that models can truly be generalized and used to predict new observations. So if I were to repeat this analysis, I might split up the training data set into 400 randomly selected training observations for each of the models, and then test within the training data. And then use the 258 holdout for the ensemble.